This video was a brief introduction to buffers and buffer systems. When we think of a buffer, we may think of something that protects us or keeps something away from us, something like a buffer zone. But if we think of it this way, let's think about a buffer as something that lessens the effect of something or protects us from such an effect. When we talk about a buffer system in chemistry, we're talking about something that protects the system from large changes in pH. That is to say, we're going to allow the system to absorb significant amounts of either acid or base and keep the pH from changing radically. We want to have a change in pH that is less than 1 unit in either direction. So a change in pH of less than plus or minus 1 units. We can construct one by placing a significant amount of both members of a conjugate weak acid-base pair into solution. Now, because we have both an acid and a base, that means we've got an equilibrium, and Le Chatelier's principle will then allow such a system to absorb a significant amount of added acid, strong acid, or added strong base, while maintaining essentially the same pH. Buffer systems are of great import both in laboratory chemical situations and particularly in biochemical or biological chemical situations. For instance, our human bloodstream is buffered with the carbonic acid bicarbonate system, which keeps our blood pH at about 7.35. The chemistry here is this: carbon dioxide dissolves in water. Okay, carbon dioxide dissolves in our bloodstream and we get carbonic acid. Then this equilibrium is established between carbonic acid and its conjugate base, the carbonate ion. That means if I add acid, this equilibrium, if I add acid, then the equilibrium is going to shift to the left. If I add base, then the equilibrium will shift to the right. But Le Chatelier is going to then, the Le Chatelier principle and equilibrium then allows that essentially to maintain a balance, and this number, the concentration of hydronium, will essentially be constant. So let's look. Remind ourselves, here's a generic acid dissociation equilibrium. Here I've replaced the symbol HA with the word acid and the symbol A- with the word base because that's what they are. This is a weak acid and this is its conjugate base. If I put that into Ka, okay, the equation is the same. I'm just using different symbology. I can solve that for hydronium and we get what I call the buffer equation. The hydronium is equal to Ka times acid over base. Now notice, the larger acid is, the larger hydronium is going to be. So again, more acid, and that makes good sense. The more base we have, the smaller this is. So the more base, the less acidic it is. If I take the logarithm of both sides, actually take the p function of both sides, we get this equation, which is known as the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation indicates that if we have equal concentrations of acid and base, okay, so if acid concentration is equal to base concentration, then acid over base is equal to 1, and the logarithm of 1 is equal to 0, and therefore the pH is going to be equal to the pKa of the weak acid. This logarithmic dependence also tells me that the pH will stay the same until 90 or more % of the acid or base up here is converted to its conjugate. That means such a system would be able to absorb a significant amount of either a strong acid or a strong base and still stay within 1 pH unit. The amount of strong acid or strong base that a buffer can absorb until it changes by 1 unit is called the buffer capacity. In general, we find this: the more concentrated the buffer, the higher the buffer capacity. Here's an example. So suppose a buffer system contains 1 mole per liter each of acetic acid and sodium acetate, its conjugate base. It would have a pH of approximately 5 because the Ka for acetic acid is 1.78 times 10 to the minus 5th, and so the pKa is 4.75, or approximately 5. Such a system would stay at approximately 5, pH of 5, until essentially 0.9 moles, 90%, of either the acid or the conjugate base was consumed by the addition of a strong base or a strong acid. We can construct a buffer at virtually any pH we want by simply selecting a weak acid then with the appropriate Ka. Pardon me, that should be a capital K. Ka. The desired pH is matched with an acid and its conjugate with the pKa equivalent to the pH that we desire. Let's look at an example problem. The problem says, circle the best acid in the table above to create a buffer with a pH of 4.3. So, here's our answer. We look for an acid. We look for an acid with a pKa of approximately 4.3. And there's our answer. Our answer is C6H5CO2H. That's benzoic acid. Okay, its pKa is 4.19. Okay, so if we wanted to buffer it at 4.3, we'd start with benzoic acid. Because we want a slightly higher pH, we'd have a little more base than we had the weak acid. So here HA is going to be C6H5CO2H. What's the conjugate base of that? Well, let's pull off a proton, C6H5CO2 minus. This is benzoic acid, and this is the benzoate ion. There is more that we could talk about. I could show you buffer activity, but for now, let's just know this. If I have both members of a conjugate acid-base pair in solution, I will have a buffered solution. It will be resistant to large pH change, even with the addition of small amounts of strong acid or strong base. And the essential pH of that buffer will equal the pKa of the acid that we choose. That concludes our introduction to buffer and buffer systems. If and when you need more information, you know where my office is and you know where to find me.